Hello students, this lesson is U5A01b2. In this lesson, we are going to be talking about dilating a line on a coordinate grid. Okay, so let's take a look. So suppose I give you the situation where we have a line is given by this equation, y equal to 2x minus 1, and I am asking you to dilate that line over the point negative 2 comma 1. So in doing so, you'd expect that the line to enlarge, right? Given the definition that I gave you in the previous video about, what it means to dilate something. And yes, you're right. However, if you think about this, it's kind of, there's something confusing about this. And that is a line, wait, doesn't a line extend forever? It does, right? So when we're dilating something that extends forever, that has no size limit, like how does that even work? So for that reason, this topic, it actually baffles me a little bit. However, this is a topic that is covered on the region, so I have to go through this. Otherwise, this would be a standard that, we would have missed in this course. So here we go, okay? So we're going to approach this kind of problem in the same sense that we did in the previous lesson. And that is, we're going to plot out y equal to 2x minus 1 on the grid. And then we're going to plot the center of dilation, negative 2 comma 1, and then we're going to dilate the line. Now, in order for us to do this, though, we need specific points that are on the line 2x minus 1 to perform the actual dilation with, because that was the technique that we had used in the previous lesson. So let's do that. So I know that 2x minus 1, has to pass through 0 comma negative 1. And I also know that 2x minus 1 has to pass through 1 comma 1, because if I start from 0 comma negative 1 and apply a slope of 2, I'm going to go over 1 and up 2, and I will end up at 1 comma 1 there. So what I'm doing, okay, is I'm going to take these 2 points that are here, and I'm going to be dilating not the entire line, but the line segment. And this is the approach that I'm going to take to solving this problem. I am going to dilate this line segment over this point, the center of dilation. So how am I going to do that? Well, I'm going to approach it the same way I did. I'm going to connect the points that are on the line to the center of dilation. And then I'm going to, however much distance I am away from the center of dilation, I'm going to move away from that given point here. So notice here I have 3 units away from the center of dilation. I'm going to move 3 units away. I'm going to, and again, I'm going to dilate this point over here by a factor of 2. So I'm going to move down 2 and over 2. So from here, I'm going to go down 2 and over 2 and end up over here. So hence what I end up with is I will end up with a line that looks like this. And this is, in a sense, a line that is a dilation of 2 of the original. However, again, like I said before, it's kind of silly to think of this as a dilation when a line, the very definition of a line, there's no bound, right? But anyway, this is something that they asked for in the region, so that's why I'm telling you this is the approach that you're going to take, okay? So when we dilate these lines, okay, over the center of dilation, we approach it the same way. We just need to select different points that are on the original line, and we're going to dilate that line segment to produce the image that is the dilation. So what exactly is the equation of this line then, right? Of the line that we just graphed. What is the equation of this line? If you notice here, okay, these 2 lines happen to be parallel. So the line that we are dilating, the image of that line will have the same slope. They are going to be parallel. All right, that is important to know. And well, in order for us to find out what the equation of this line is, okay, we also need another point though. Well, we can select from either the point up top or from the point below, okay, and we can just simply substitute it in to writing the equation of a line in point slope form, and that'll be it. you don't have to go any further. But if the problem requires you to rewrite this in in slope-intercept form, of course understand that all you have to do is just distribute this and combine like terms. So it turns out to be 2x minus 7. So again, notice that the length of the line segment after the dilation compared with the line segment formed by the initial 2 points we found for the given line, that the line segment is in fact doubled. Let's try this again, okay, for a dilation of by a scale factor of 3 for the given line. See if you can figure this out. Pause the video and try this out on your own. So again, hopefully you guys had some time to think about this. I'm going to plot this line on the grid, and I'm going to plot that point on the grid as well. So if I do that, I'll end up with a line that looks like this. I know that this line here has to pass through 4, 1, which I put over here. And I know that this line has a slope of negative 1/3, which I'm going to go up. I'm going to go down 1 and over 3, or I can go up 1 and over to the left 3. So the other point has to be 1, 2. Just a comment on strategy here. The points that I choose, do you think the points that I choose on the given line, should I choose points that are far away from the center of dilation, or should I choose points that are close to the center of dilation? Which one do you think would serve you better? Well, if you're thinking that selecting points close to the center of dilation, you're absolutely right. And the reason why you want to select points close to the center of dilation is because it will make drawing things more manageable. Just imagine this with me, right? If the point that you select on the line ended up being over here, and you draw the connecting line, the construction line connecting the center of dilation to the 2 points, you're going to end up with a really big graph. So to avoid something like that, okay, it would actually, to your advantage, select points that are relatively close to the center of dilation. Anyhow, so we're going to now dilate this by a factor of 3. And in order to do this, okay, we are going to again connect the center of dilation to the 2 points. And by doing this, okay, notice now I went over to the left 1 and down 1. So I need to go from here over to the left 1, down 1, over to the left 1, down 1. So now I have a scale factor of 3. Same thing over here. I'm going over 2 and down 2, over 2, down 2, over 2, down 2. I have my point over here. Recognizing that the slope between the 2 lines must remain the same, all I got to do now is just pick either the point on the left or the point on the right to write the equation of this line, and it is just as simple as that. The equation of the line that's dilated is simply negative 1/3 x minus negative 1 plus 0, or simply y is equal to negative 1/3 x plus 1. If you want to rewrite it in standard form, you can also multiply both sides by 3 and bring everything over one side. But again, odds are on the regents, this is probably where you can end, okay? But this is just another way of writing that same equation in standard form. Let's take a look at the next problem. All right, so here you're given an equation in standard form, and what you need to do is you need to dilate this by a factor of 3/2, and we're going to find out what the equation is. Now, when you're doing this, okay, there's no mention of where the center of dilation is, so by default it would be over the origin. So let's first plot this thing out. Now, standard form of a line, okay? One of the advantages of working with an equation in standard form is you can easily figure out the x and y intercepts. So if you recall, well, yes, standard form, we should be flexible in knowing how to graph and interpret the line with the x and y intercepts. So here, if you look at this, x plus 3y is equal to 6, okay? At the y-intercept, okay, the x-coordinate must be 0, isn't that right? So if x was 0, then that means the y-coordinate on the y-axis must be positive 2. The x-intercept, the y-coordinate must be 0, right? So if the y-coordinate is 0, that means the x-coordinate must be 6. So that means my line must pass through in this manner here. So the equation, or the line when graphed, looks something like this. So and notice, okay, I am 2, so this point right here is 2 away from the origin, and this point right here is 6 away from the origin, as I've indicated in the diagram. Okay, so now we want to dilate this by a factor of 3/2. In other words, 1.5. Okay, so let's think about this. I'm going to take this number here and this number here, and I'm going to multiply it by 1.5, just like I did in the previous examples. So what is 1.5 times 2? Well, you're thinking 1.5 times 2 is 3. You're absolutely right. What is 1.5 times 6? If you're thinking it's 9, then you're absolutely right again. So my new points I'm going to end up with will end up there. So the equation, okay, one more time, okay, we're going to have the same slope. What's the slope of this line again? We're going down 1 and over 3, right? So the slope is negative 1/3. I have a y-intercept of 3. I can easily write the equation of this line. It's negative 1/3 x plus 3. Do you have to write it in standard form? No. But again, just understand that sometimes on the Regents and on many other standardized tests, and as well as when you're just problem solving in general, okay, you should be flexible in your ability to work with the equation of a line expressed in different forms. Again, notice that the length of the image compared with the length of the 2 initial points found, the image is in fact 1.5 times longer than the original. All right, so in summary, slopes of the image after a dilation is always going to be the same as the original line. The length of the image of the line segment after the dilation is always a multiple by the scale factor with the length of the line segment between the initial 2 points of the given line. Again, just to compare all these scenarios here, okay? So this was a dilation of 1/2, so therefore this is going to be half of the original. This is a dilation of 1/3, so this is going to be 1/3 of the original, okay? All sides that were dilated are parallel and multiplied by the lengths that were multiplied by the scale factor. All of these sides, okay, ended up being parallel.